I now call to order the Society's 2,481st meeting in what is now the 152nd year since its founding on March 13, 1871. Good evening, everyone.
Good evening.
And my name is Larry Milstein. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends, including everyone here in the Powell Auditorium, at the Cosmos Club, and everyone on YouTube tuning into the live stream of tonight's PSW meeting, including those nearby and far abroad. At the last meeting, viewers in Europe, South America, Asia, and Australia, as well as the US, watched the live stream. So welcome one and all, wherever you are at the moment. And speaking of YouTube, I'm happy to note that the video of Sean Carroll's lecture has now been viewed over 130,000 times on YouTube. Tonight's lecture will be by Koichi Suda on JAXA's stunningly ambitious and successful Hayabusa2 asteroid return mission. We're especially fortunate and grateful that he's traveled here from Japan to give this talk. It's perhaps worth noting that the timing is a bit fortuitous. The sample return capsule of NASA's OSIRIS-REx mission is to return home to Earth this Sunday after taking samples of the asteroid Bennu. And Yuichi will be in Utah Sunday to join NASA colleagues in watching the return. Ironically, he told me that he was not able to watch the sample return of his own project, Hayabusa2, but he is going to be able to watch the sample return for OSIRIS-REx. And the same is true for the launches. He missed his Hayabusa2 launch, but he, and as it turned out, I and Robin were present at the Kennedy Space Center for the launch of OSIRIS-REx. So, it'll be very interesting to hear from him about this wonderful and astonishing engineering achievement. The Society is grateful to PSW full-year sponsors, PSW member Mike Helton and Helton Associates, and the Policy Studies Organization in cooperation with the American Public University. We are also grateful to PSW member Tim Thomas for his generous support of the Fall Lecture Series. Mike, Tim, thank you. And we're also grateful to a sponsor of tonight's lecture who asked us not to name them, but thank them as well. I'm pleased to announce the following new members. Ahmed Lutfali, a technology entrepreneur with Zizitech, interested in cybersecurity, technology modernization, and space exploration, who learned of PSW from PSW member AC Charania, who is right here in the front row. Thank you, AC. Simon Clout, retired, interested in a broad range of subjects, who learned of PSW from watching recordings on the PSW YouTube channel. Tom Spangenberg, co-founder of Sharp Pulse Corp., with many and varied interests in science and technology, from plasma pulse power to reproductive medicine, who learned of PSW through the PSW YouTube channel. Gary Sobolewski, an attorney with Blue Origin, broadly interested in technology and science, who learned of PSW from a friend. Linda Ho, a program officer at NIH, widely interested in science, who learned of PSW from a friend. Paul Werbos, who is here tonight, a research program director at NSF, interested in a wide variety of topics in science and technology, especially climate science, who learned of PSW from PSW member Frederick Durema, who is also here tonight. Thank you, Frederica. And tonight's speaker, Yuichi Suda, who learned of PSW from the invitation to speak here tonight, and whose interest will be clear in at least some part from tonight's lecture. We welcome them all to membership. Thank you. Mark Clampin, formerly Vice President of PSW, will now present the minutes of the 2480th meeting and the lecture by Tabitha Dobson on DARPA's Draco project, prepared by Recording Secretary Cameo Lance. Mark, stage is yours.
Okay, thank you, Larry. On September the 8th, 2023, from the Powell Auditorium at the Cosmos Club in Washington, D.C., and by live stream broadcast on the PSW Science YouTube channel, President Larry Milstein called the 2480th meeting of the Society to order at 8:02 p.m. Eastern Time. It being the annual meeting, President Milstein reported the state of the Society for the fiscal year ending June 30th, 2023. He noted that membership applications and total membership increased over the previous year. Dinner attendance was back to pre-pandemic levels, but combined in-person and live stream lecture attendance still somewhat lagged. He noted that the videos on YouTube most widely promulgate the Society's programming. There are now 199 videos in 15 playlists, he said, collectively garnering over 850,000 views. Newly posted videos were viewed several hundred to several thousand times in the first 2 weeks after posting. Sean Carroll's video, he noted, had been viewed over 125,000 times, and there are now about 9,500 subscribers to the PSW YouTube channel. He reported that the audit committee had examined the books for the year, and he read their report that they found the books in order and did not find any material irregularity. He reported that the Society ended the year in black, despite the tripling of the Cosmos Club's charges, thanks, he said, to major donors and lecture sponsors, as well as dues and contributions by the membership. And he noted that the Society's reserves continued to grow and remain adequate relative to annual expenses. President Milstein then thanked PSW member Mike Helton and Helton Associates, PSO APU, PSW member Tim Thomas, and the PSW member Eric Enig and Enig Associates for their sponsorships. He then introduced new members. PSW member Erica Kane then read the minutes of the 2479th meeting and the lecture by Bill Merrill and Sam Brody on the Ike Dike project to protect Texas coasts, prepared by PSW Recording Secretary Cameo Lance, who was unable to attend the meeting. There were no comments on the minutes. They were approved by a voice vote of the members in attendance, and President Milstein announced they will be posted to the website in due course. He then introduced the speaker for the evening, Tabitha Dodson, Program Manager for DARPA's Demonstrating Rocket for Agile Cislunar Operations, known as DRACO, and her lecture on nuclear propulsion systems for space exploration. Dodson began by explaining that her talk would span many different topics, including aerospace rockets, the nuclear reactors, and a variety of political and legal issues affecting the program. She then explained that DARPA's Draco program is in partnership with NASA and Lockheed Martin, who are the prime contractors. Funding, she said, comes from Space Force, NASA, and DARPA in equal parts. She then reviewed DARPA as an organization and explained a bit about how it works. By way of introduction to Draco, Dodson then played a video of President Kennedy's well-known speech announcing the nation's goal of placing a man on the moon by the end of the decade. But she highlighted a later and less famous part of the speech in which Kennedy announced another goal, developing a nuclear rocket to facilitate man's progress into space. She explained that that goal was only partially carried out through the NERVA project that engineered, produced, and tested a nuclear-powered rocket engine. The Draco project, she noted, builds on the experience and test results the NERVA project achieved. She began the technical portion of the talk by explaining some fundamentals of rocket engines, such as the importance of a specific impulse to reduce propellant mass for a given thrust, and she reviewed differences between chemical thrusters, electric thrusters, and nuclear thrusters. She then reviewed key terms for understanding the structure and functioning of nuclear reactors, including terms describing different types of nuclear fuel, such as highly enriched uranium used in military reactors, and the kind of fuel planned for Draco, utilizing low-enriched uranium embedded in a matrix. Dodson then explained some fundamentals of nuclear thermal rocket construction and performance, explaining the pump, turbomachinery, the reactor core, the fuel, and its geometry and methods for controlling thrust. Next, the speaker reviewed key differences between terrestrial nuclear power and nuclear thermal rockets. One key difference, she said, is the operating core temperature. Terrestrial reactors operate between 300 degrees Celsius for pressurized water reactors to 1,000 degrees Celsius for gas-cooled reactors. Nuclear thermal reactors for space propulsion will operate at much higher temperatures, around 2,500 to 3,000 degrees Kelvin. She then reviewed the basic operation of nuclear thermal rockets and showed diagrams of the fuel and the control tube assemblies and of the general layout and operation of the reactor. She reviewed the basic fission process, emphasizing that nuclear fission is a fairly well characterized problem of statistics, with the goal of increasing the population of neutrinos in one concentrated area and influencing the energy distribution of the neutrons there to increase the probability of fusion. The speaker then turned to the Draco program itself. She started by highlighting 5 operational guide rails and goals of the program. Conduct no full power tests on the ground, utilize cryogenic liquid hydrogen, use high assay low enriched uranium fuel, known as HALBU, launch in 2027, and focus on collecting data for HALBU fueled reactor characteristics and performance. She explained that DARPA is particularly interested in understanding thermal feedback effects, which will likely occur and can then be studied at startup of the Draco engine. She reviewed the possible preliminary Draco test matrix and discussed examples of preliminary engine startup results, including general design criteria. The speaker then discussed the status of the program and the milestones the program is expected to reach in the future. Dodson concluded the lecture by enumerating some of the benefits of nuclear thermal rockets. She said in particular that they can deliver heavier payloads, deliver payloads faster, perform more maneuvers, and maneuver more aggressively. After the lecture concluded, there was a question and answer period. One member asked what the drums are and why rotating them is so exciting. Dodson responded that the drums are long beryllium cylinders with asymmetric inner coatings, so that in one orientation they primarily reflect neutrons, and in the opposite orientation they primarily absorb neutrons. Thus, a relatively simple rotation of the drum reorients the beryllium cylinders and moderates the intensity of the fission reaction in the uranium fuel. Another member asked what it would take to turn a nuclear thermal rocket engine into a power source. The speaker explained that the coolant loop for the propellant would be used to cool all of the various constituent elements. So the coolant would go in a tie tube and out of the core and eventually back down to the fuel. However, for a power reactor, it would only go through the tie tube and not through the fuel. After the question and answer period, President Milstein presented the speaker with a copy of the announcement of her lecture, signed by the General Committee, a PSW ribbon, and a copy of Volume 1 of the PSW Bulletin, signed on behalf of the members. And he thanked the speaker for spending her time with PSW and for giving the lecture. He then made some housekeeping announcements, discussed upcoming lectures, and invited guests to join the Society. He adjourned the meeting on vote of the members present at 9:38 p.m. Temperature in Washington, D.C., 22 degrees C. Weather, cloudy. Live attendance, 117, 66 in person, and 51 viewing on YouTube. Views of the video recording on YouTube in the first 2 weeks after the lecture, 778. Respectfully, Mark Clampin, on behalf of the Recording Secretary, Cameo Lance.
Thank you very much, Mark. Are there any corrections? No corrections. Any comments? No comments. Well, hearing none, I'll entertain a motion to accept the minutes as read. Second? All members in favor of accepting the minutes as read? All members opposed? The minutes are unanimously accepted as read and will be posted to the website in due course. Oh, sorry, I forgot to put that slide up. Okay, let's move to the present. We now turn to tonight's lecture by Ryuichi Suda on JAXA's highly successful and still ongoing Hayabusa2 mission. Surveys and samples from Asteroid, Ryugu, and beyond. It's worth noting that Hayabusa2 has been spectacularly successful both in its engineering and its sample return and the science it is supporting. As you will hear, the mission combined multiple spacecraft and sample collection modalities, as well as a suite of remote sensing instruments, and it involved complex maneuvers and trajectories at Ryugu and to return to Earth, and now to proceed to its next objective. Truly a tour de force of space exploration, engineering, and execution. Yuichi is currently the team leader of the Hayabusa2 extended mission and professor in the Institute of Space and Astronautical Science at the Japanese Aerospace Exploration Agency and in the Department of Aeronautics and Astronautics in the Graduate School of Engineering of the University of Tokyo. Yuichi led the development and operation of the Hayabusa2 mission, serving as chief engineer and as project manager. He also, incidentally, served as deputy lead of the Icarus mission, the world's first interplanetary solar sail. Among other honors and awards, Yuichi's team received the IAA Laureus Award, the Aviation Week Laureate Award, the Japanese Prime Minister's Commendation, and the IAF World Space Award. Yuichi earned his undergraduate and graduate degrees, including his PhD in aeronautics and astronautics at the University of Tokyo. And before turning the stage over to Yuichi, I want to thank him for traveling from Japan to give this talk, and I want to thank the team at JAXA, some of whom are in the audience, for their terrific help in arranging for him to be here with us tonight. All questions will be fielded after the lecture during the question and answer session. Yuichi, stage is yours.
Okay. Sure. Okay, good evening. And thank you very much for very detailed introduction, Larry. And thank you very much for inviting me to this distinguished and historic places. And I'm very honored to speak in front of all of you, these distinguished guests here. So my name is Yuichi Tsuda from Japan Aerospace Exploration Agency. And this is a talk about Hayabusa2. And I have been taking a role of the Hayabusa2 mission as the project manager. And this is in this talk, I would like to cover the story and the significance of the Hayabusa2 mission and its scientific outcomes. And First of all, let me introduce about my background. I am a professor in the Department of Aerospace Flight Systems in ISAS, so I am engineer. So my field of interest is astrodynamics, spacecraft guidance, and navigation and guidance and control of spacecraft, and all solar system exploration. So besides leading the project team of this mission, I led the spacecraft design and orbit design, which was, more fun for me than management. So today I will try to tell you how exciting the sample return mission is, both from engineering and scientific aspects. But please excuse me that you may feel my excitement is more on engineering side, because it's really exciting. So let me start from this one. Yes, it's moving. So this is a movie from the second touchdown. And on board the sampler home monitor camera at the time of the second touchdown, this is the moment of the final freefall descent and the touchdown ground, and retrieve the samples and ascended away. And what we are proud of about this movie is that this is the second landing, which means that we did landing twice in the same asteroid, but with the same spacecraft. Moreover, the second touchdown tried to get the subsurface material, and I will touch about this more in detail later. So, actually surprisingly, even to us, the landing positional error accuracy was as small as 60 centimeter, 2 feet. Thinking of the distance between the Earth and the Ryugu at that time was 300 million kilometers away. So this level of accuracy is more than satisfactory for us. Okay, so although we faced many hardships during the asteroid proximity operations, we overcame all, and Hayabusa2 finally returned to Earth in December 2020. So this is the landed re-entry capsule here with the parachute deployed on the Woomera Desert, South Australia. So before going into the main story, let me briefly introduce about the Japanese space exploration programs. And this chart is summarizing the Japanese lunar and planetary missions program. The first planetary mission or deep space missions of Japan were Sakigake and Suisei, which are here, which went to the comet Halley in 1985. And these missions were followed by Hiten is here, which went to the moon, and Mars Explorer Nozomi, which actually unfortunately failed to be inserted to Mars orbit. And then Hayabusa, which became the world's first successful sample return mission beyond the moon. And in 2010, we embarked on planetary missions to various celestial bodies, such as Kaguya to the moon, and the Akatsuki to Venus, and this one is a technology demonstration mission Icarus, which became the world's first successful sample return mission. World's first interplanetary solar sail mission, which I led as a deputy project manager. And then a follow-up mission to Hayabusa is Hayabusa2. And we also have multiple ambitious plans in 2020s, including the landing on the moon and Mars moon sample return and the comet high-speed flyby. So Japan has a long history of the interplanetary science missions, although the number of missions is not so high, of course, compared to NASA. But the program effectively and efficiently contributed to the evolution of both the spaceflight technology and space science. Okay, then about Hayabusa2. Hayabusa2 is the second sample return mission for us, and this is the world's second sample return mission to asteroids, following the first Hayabusa. And Hayabusa2 was launched from the Tanegashima Space Center, which is a southern island in Japan, in 2014, and explored an ever unexplored asteroid Ryugu around 2018 and 2019, and successfully returned to Earth with the Ryugu sample in 2020. So the key features of the mission are like this. So first, it's a round-trip mission, and enabled by the high specific, which means a high efficiency ion engine system with the continuous thrust cruising. And the second, the spacecraft is going to stay around the Ryugu for 1.5 years with the 4 landers and 4 science instruments. And the biggest highlights of this mission is the touchdown, of course. And the spacecraft was designed to have a capability of 3 landings to the surface of the asteroid. And out of that, 2 of them are what we call normal touchdown, and the third one is a pinpoint touchdown. But in reality, because we faced very, very severe difficulties due to the harsh environment of Ryugu, we changed the strategy to land there twice, only using the pinpoint touchdown. And I will tell you about that later. And another highlight is the artificial crater generation. So by the kinetic impact technology, by doing so, not only the surface of the Ryugu, but also the subsurface structure can be acquired. And what we actually did is we could make the 18-meter diameter, very large artificial crater on the surface of the asteroid. And after that, we could touch down in the edge of the crater and get the subsurface material from there. Okay, so let me slightly mention about the scientific objective as well. The target of the Hayabusa2 mission is the asteroid Ryugu, which you may know that the solar system is full of asteroids, and it counts up to around 1.3 million to date, and discovered by the Earth-based telescopes. And the Ryugu is among them a very interesting asteroid in a sense that it is estimated to contain water and organic compound. So there are such asteroids in far distance, such as in the main belt or in the asteroids beyond Jupiter. But this Ryugu is flying just in between the Earth and Mars region, so it's very close. So it's reachable with the current technology, our technology. And then scientifically attractive as it contains material related to life on Earth. So if you look at the universe through this special asteroid Ryugu, then you can understand not only about the Ryugu, but also about the history of the solar system, and also we can expect to get some clues to the origin of life on Earth. So bringing the sample Ryugu back to bringing the sample of Ryugu back to Earth should be the most effective and attractive way to realize this scientific goal. Okay, so the mission scenario of Hayabusa2 goes like this. So it's a 6-year mission launched in 2014, and after 3.5 years of cruise, then it will arrive at the Ryugu in 2018. And after that, we'll stay there for 1.5 years doing many challenging operations like landing the rovers on the surface of the asteroids, and also the spacecraft itself will land on the surface twice. And in between that, we did the kinetic impact mission to make a crater, or make a hole on the surface of the asteroid. and so on. And after doing that, then we left there in November 2019, and after 1 year, we returned to home. We returned to Earth in December 2020. And the appearance of the Hayabusa2 spacecraft looks like this. So it's a very compact spacecraft, having only about 600 kilograms. So if compared to Osiris mission, it's a 2-ton mission. So it's like a bus versus compact car, economy car. So the tip-to-tip span of the spacecraft is 6 meters. And Hayabusa2 is a solar electrical propulsion mission. So it's equipped with a high specific impulse or high efficiency ion engine system with 60 kilograms of xenon fuel, which corresponds to about 3 kilometers per second orbital acceleration capability. So thanks to this technology, we could carry as many as 14 scientific instruments to cover various types of in situ exploration activities packed into this very compact spacecraft. And one of the interesting features of the engineering-wise is that Hayabusa2 is dropping many things. So it brought as many as 12 deployables to space. Rovers, landers, and a kinetic impactor and artificial navigation landmark called target markers. Most of them were separated around Ryugu for the each of the specific missions. And except for, of course, the re-entry capsule, that should be separated near the Earth. So which are all successful. And as I said, the Hayabusa2 is a solar electrical propulsion mission combined with the, and actually it is combined with the Earth's gravity assist. And the left figure here is the forward trip utilized to show it is showing the Earth swing by plus the gravity assist. And the right figure shows the return trip, which shows a direct flight from the Ryugu to Earth without the gravity assist. And one of the technical highlights of this mission is that as I said, we use the ion engine as the main propulsion system, and which is very high efficiency, but is very low thrust, only having 30 millinewton, which corresponds to 3 grams of the thrust. So you cannot launch this spacecraft with the ion engine from the ground, from the Earth. But once you go to the space, then the small, even though the thrust is very small, it can accumulate it to the very large acceleration. So the efficiency does matter. So the efficiency, the fuel efficiency is 10 times higher than the ordinary chemical propulsion, chemical rocket engine. So that's why we could carry only 10% or 60 kilograms of the fuel in the 600 kilogram spacecraft. And because the thrust is very small, the thrust of firing have to be continuous. And actually, out of 4.5 years of the cruising, forward and return trips, 1.5 years were the propulsive flight, and other 3 years was the ballistic flight. Okay, so Hayabusa2 arrived at Ryugu on June 27, 2018. The appearance of Ryugu was very interesting, full of discoveries scientifically and the hopelessly harsh environment engineering-wise. It was revealed to be a top-shaped asteroid with the diameter of about 900 meters. So it's a very small asteroid. And Ryugu has a retrograde rotation with a period of about 7.6 hours. So about 3 times faster than the rotation of the Earth. So and the Ryugu is very dark asteroid, having only 2% reflectance factor. This is one of the typical characteristics of a carbon-rich asteroids. And this very dark, low reflectance surface property actually caused several errors and operation aborts in some of the critical operations of Hayabusa2. But there was a worse source of headache in Ryugu. The biggest headache for us was that Ryugu was covered with full of boulders all over the surface. So it looks like a homogeneously rocky, homogeneously bumpy surface. And we could not find the good place to land because of that. And we were obliged to improve our landing performance from the originally designed 50-meter accuracy to finally 1-meter accuracy. And this chart shows the geometry of the basic asteroid proximity operation strategy. The spacecraft basically hovers 20 kilometers above the asteroid along the asteroid Earth line. So asteroid Earth line is here, and the spacecraft is staying almost always 20 kilometers above toward the Earth. And sometimes it can move horizontally like this to observe the asteroid from the side or from the top to change the direction of observation. And the spacecraft Earth distance at this time was 240 million to 300 million kilometers, which corresponds to about 13 to 20 minutes light time. So the spacecraft had to do the guidance and navigation, everything in autonomous. If the spacecraft wants to go below 500 meters. So for touchdown or very low altitude observation, the spacecraft is switched to the full autonomous. So the spacecraft, so we started the detailed observation after the arrival. And one of the exciting part of this mission is that we have many international friends, colleagues, to discuss with. And this is a photo from one of the project's most critical, or biggest meeting held after the arrival to select the landing sites for the spacecraft and 3 rovers. For this meeting to be successful, we had done the data analysis and decision-making training for 2 years before the asteroid arrival, making sure that the team from different countries and groups could handle the sample data the same data in the right way, exchanging quantitative and very delicate analysis results appropriately, and to be able to reach the consensus rapidly. This LSS meeting, landing site selection meeting, was held just 1.5 months after the Ryugu arrival, thanks to the training, and participated by more than 100 scientists. And we could derive a set of landing sites candidates very, very smoothly. But only one element which was not smooth was the terrain of Ryugu. So human side was very smooth, but the Ryugu is not smooth. So therefore, we imposed ourselves a lot of homework to refine our landing accuracy. We cannot refine the surface of the asteroid, so we have to refine our side, the landing accuracy, to adjust to the Ryugu environment. So this is the scene from the press conference right after the LSS meeting. And the leaders of the Hayabusa2 international team are all here, including from the left, the Dr. Aurélie Moussi from CNES, the French Space Agency, and the Terami Ho from the German Space Agency DLR. And those two are the project manager of the mascot lander. And also we have a project scientist, Dr. Watanabe, in the middle. And we held this kind of press conferences every 2 weeks during the proximity operation phase. And for each press conference, key scientists and engineers attended to explain about the new findings and the new plans, and sometimes the challenges and difficulties we are facing. So a space agency usually doesn't like to tell about the uncertainty or failure probability of the project, but we try the press conference to be a place to make the general public feel a sense of togetherness by disclosing our challenges. And this really helped stimulate the general public, and I think Hayabusa2 mission was so successful also from the aspect of the public relations. Okay, so the first thing we did as a critical operation was to deploy the 3 rovers based on the landing site selection meeting result conclusion. And the first 2 were the Minerva 2-1. It is on the left. It's a twin rover separated at once. And the second one was a Mascot, which is a 10-kilogram box-shaped lander developed by DLR and Kunes. And those are movable like this. They can hop and they can jump to change the place. So it's not just a box. So you can see a very black and black world observed by these rovers. And actually, the rover scientific instruments were not only camera, although the camera is the results are all the most spectacular, but it actually includes temperature sensor, magnetometer, infrared spectrometer, and so on. So many instruments are there. Okay, so the rover operations were all successful. Now the problem is, how can we land the spacecraft to Ryugu? So as we increased the resolution of observations, we got to know more the severeness of the terrain environment. The original specification of Hayabusa2 was that the landing accuracy was 50 meter, which means plus minus 50 meter. So we needed a 100 meter diameter flat surface on Ryugu, or safe surface on Ryugu. But you can see here that there are too many rocks so that we could not find 100 meter safe place. So still we had to find a place to land because Hayabusa2 is a sample return mission. So returning without sample was not an option for us. In fact, this process took an additional 4 months. And let me skip this step-by-step processes as time is limited today. But finally, we found the 20-meter diameter relatively flat surface shown as an orange circle on the right figure. And you can see you see the image is just outside the circle. Outside the circle, you can see very big rocks, dangerous rocks, and within the circle, the surface looks fairly flat. But the diameter of the circle is only 20 meters, which means that the spacecraft has to land with the accuracy of 10 meters. That's beyond our specification. So we plan to do the experiment to measure our actual performance. And for that, what we decided to do was to drop an object to the ground instead of landing the spacecraft itself, and evaluate how precise we can physically place an object to the Ryugu ground. And for that, we used the target marker. So this ball is a target marker. It's a 10-centimeter reflective wall illuminated by the flashlight at the bottom of the spacecraft. And it works as the visual landmark. So Hayabusa2 was equipped with 5 target markers, and we used one of them for this testing. And we tested the landing accuracy by throwing the target marker to the ground instead of landing the spacecraft itself by using the same guidance scheme. And the result is here. So this is a 20-meter circle, and we tried to throw the target marker to the center of this circle. So can you find the target marker? Which is here. So although it's difficult for your eyes to locate it, Hayabusa2's image processing can precisely detect it. And we throw the target marker to aim at the center of the 20-meter circle, and the result was that target marker was settled 15.4 meters off from the center. 15.4. That was actually a very good result, wasn't it? compared to the engineering specification of 50 meter. So 3 times better than the specification. So engineers were somewhat happy about this result. But you know, this result means that the landing precision is not sufficient to conquer Ryugu. So, but there was one more good news. We actually attempted another guidance test to chase the falling target marker using the onboard autonomous navigation and guidance system, like this. So this, you can see a bright dot in the center of the movie, which is a dropping target marker observed from the onboard navigation camera. As the spacecraft is trying to chase the target marker by lateral thruster firings, the target marker is eventually converged to the red target control box. So it's still converged, so now it's converged like this. The corresponding size of this red box is 1 meter on the terrain. This means that regardless of the terrain condition, once the spacecraft can detect the target marker, it can precisely locate and guide itself with a terrain relative accuracy of less than 50 centimeter. So now we got the confidence for the target marker tracing capability. So we decided to make full use of the target marker to realize what we call the pinpoint touchdown. Originally, we didn't think to use the target marker like this. The original plan is on the left of this chart, and the modified plan is on the right. Originally, target marker was to be separated from the spacecraft just before the touchdown during the final descent toward the ground. And the purpose of it was to completely eliminate the terrain relative velocity at the touchdown, which was essential for the safe landing to unknown terrain. However, based on the successful result of the target marker dropping operation, we changed the strategy to utilize the already dropped target marker as the visual landmark. So not only controlling the relative velocity, but we decided to try to control the relative position as well. And for that, we survey the terrain around the dropped target marker and find a safe place. Then, using the target marker, the spacecraft tries to land on the pre-surveyed safe place using the already dropped target marker as the landmark. Okay, now the problem is there a safe place near the target marker? So this is a mosaic images around the candidate landing sites captured by the Hayabusa2 onboard camera. And here is the target marker, already dropped target marker. And you can see many circles and values on the image, which shows the height information of the rocks in centimeter. So, and the red and pink circles are dangerous rocks. And yellow is marginal, and the blue is safe ones. So you can see many, many dangerous rocks, even around the target marker. And to use the target marker as a visual landmark, the landing target should be as close as possible to the target marker. You know. And where do you think is the best place to land? We actually found 2 candidates. One is within the original 20-meter circle, the orange one, and now drawn with the red zone. And it is about 15 meters away from the target marker, but the size is relatively large. Another one is a green zone, which is only 4 meters away from the target marker, but has only 6-meter diameter, or 6-meter span. And our conclusion was actually to choose the green one, this one. Although it is very narrow, having just the same size as the span of the Hayabusa2, but we evaluated that we could achieve less than 3-meter precision landing to the green zone. On the other hand, the red zone was a little bit too far, and landing accuracy to such far distance would get very bad. So the resulting sequence became like this, and we reprogrammed the landing sequence of the spacecraft. Actually, the onboard guidance computer of the Hayabusa2 is very flexible and is equipped with a kind of high-level programmable sequencer. So we reload it to implement the sequence. As the round-trip light time at that time was 40 minutes, ground-based guidance is not possible at all. Everything has to be autonomous. At first, spacecraft hovers at 45 meters, and after finding the target marker, it is to make a dive to 8.5 meters, watching the target marker. And then, because we want to land not on the target marker, but 4 meters northeast of the target marker. So Hayabusa2 is to move horizontally from here to here, while using the target marker as a visual landmark. And then, after everything is converged, it is to make a free fall to the landing site. And we uploaded this new sequence to the spacecraft and sent a go command to the spacecraft on February 22nd, 2019. So let me show you the actual results. So I'm sure engineers in engineering, the audience who has an engineering mind, love this kind of movie. Okay, here we go. So this is the movie of the target marker relative guidance at the touchdown, actually used for the onboard real-time navigation. So from the 45-meter, spacecraft finds the target marker, which is now at the center, the central bright spot, and dive into the 8.5 meter like this, and try to converge that to the center of the field of view, and then move horizontally by switching the target like this. Then spacecraft tries to move horizontally like this, and then converged. And then finally, after this, the spacecraft will make the free fall to the just below, which is the landing target. So this is the actual movie, also the actual movie of the final free fall on the landing from the first touchdown operation. And the sampling process was all successful. At the moment of the touchdown, the projectile was ejected like this, and some portion of the reflected samples are collected through the sampler home and finally stored in the sample container located at the root of the sampler home. And isn't it beautiful? Yeah, this is actually one of the loveliest movies also for me throughout the entire Hayabusa2 mission. And this should be also beautiful pictures. And this was taken in the control room right after the success of the first touchdown. There were about 50 people in the control room there, but we have actually more members outside the control room. So the total number of the project members was about 600. And it's a big team consisting of JAXA staff and university and institute researchers, industry partners, and also the international partners, and also students. And so to manage such a big team, it's quite important to share the goal precisely, and as well as rational management and positive atmosphere for challenge. Challenge here, of course, includes failure and learning. And sense of unity is in a very high level acquired through training is also important. So let me show one typical example of team building that we did actually applied for the Hayabusa2 team. We conducted what we call the real-time integrated operation training before we arrived at the asteroid. And this is the control room, and normally it's connected to the space asset like Hayabusa2. But in the training session, we connected the control room to the room right next to the control room here, which is an examiner's room. And in the team, we call the God's room. And on the other hand, the control room was called the world of mankind. And in the operation room, so the reason why we call this the God room is that because examiners can cause any breakdown or troubles by setting the simulator intentional errors, or sometimes even physically disconnect some of the cables. And in the operation room, such a sudden trouble would cause confusion and panic. And that's interesting to see from the God side. The controllers are forced to make immediate decisions, sometimes even brave decisions to abort a landing. So such troubles were caused many times in one training session. At first, the human world tries to respond to gods in good faith, but as such tinkering continues, some say, hey, this is unrealistic, this is impossible. Why is it such a bad hardware that we make, or something like that? And some even speak evil of God. But in this way, the team members can learn how useless the manual is and how the human should respond and even take predictive actions against such troubles. And youngs learn from seniors more efficiently, and sometimes vice versa, young operators can act better than senior operators and can teach the seniors. And many simulations occur all over a team, and finally the human world comes together against God and makes real good teamwork. And the rightmost poster here is the training score hung in the control room. It's a big poster, and showing that out of 44 training sessions, actually each of the sessions took about 48 to 72 consecutive hours. So that's a really busy and intensive operation. And out of 44, 22 were failed, which means that crashed onto the simulated asteroid. So about 50% of the training were failure. So what I wanted to emphasize here is that a failure experience makes the team tolerant, adaptive, and unified. For projects with huge flexible and the uncertainty, teamwork should be positively included into the quality of the mission management. And the human factor is an important element of team building, and for that, sharing the failure experience among the team is very effective, and how you can build in the opportunity to fail should be a key to a reliable system. And eventually, human worlds noticed how good the teamwork they could make, and they felt grateful to the God. And eventually, God joined the human teamwork. Okay, so now we succeeded in the landing. Is it now the time to return to Earth? Actually, no. Hayabusa2's story is still before the climax. So just 1 month after the success of the first touchdown, we attempted another ambitious mission, the kinetic impact. A device just separated from the spacecraft is called SCI, or Small Carrier Impactor, and this will soon detonate. And before that, Hayabusa2 rushed to the backside of the Ryugu to avoid damage by the explosion. And then SCI detonates like this and makes an artificial crater. So this system can accelerate a 2-kilogram pure copper bullet to 2 kilometers per second instantaneously. The reason why we use the copper is that the pure copper is not existent. It does not exist in the natural world. So we can, in that way, we can avoid a contamination. And as we may plan to collect the sample from the artificial crater afterward. And because the spacecraft had to escape, it cannot observe the impact process. That's a pity. So on the way of escaping, Hayabusa2 deployed a remote camera called DCAM-3. And it's like a Kokan shaped and works just like a single-use disposable camera, only to shoot the cratering process like this. And before damaged by the impact, the fragments, DCAM-3 transmitted the image data to the mother spacecraft. And it was really an acrobatic mission, but we succeeded, like this. So you can clearly see the big impact process observed from the DCAM-3. The impact ejector could be observed for more than 5 minutes. So it was actually a very big process. And height of the ejector reached up to 40 meters, so it was a very big reaction. It was surprising for us. And furthermore, the spacecraft could go back to the vicinity of Ryugu again and observe the terrain and compare the terrain before and after the impact like this. And scientifically, this is very important. And also analyzing the impact response led to deriving the cohesive strength of the asteroid surface, which in turn resulted in deriving the surface age of Ryugu. And it was derived and published on Science Journal that the original theory suggested about 160 million year surface age, which is overwritten or corrected by this experiment alone to 10 million year by analyzing the relation between the energy input by the kinetic impact and the size of the resulting crater. So the surface of Ryugu is found to be very young, actually, and variable. So as soon as you do something like this, TV stations want to make a full-scale set. So this is a full-scale set of the artificial crater based on actual observation data made by Japanese broadcasting company, NHK. So the diameter is 18 meters and the depth is 3 meters. And you can feel how big a crater we created. So the next thing we wanted to do was, of course, why not dive into the crater we made to get the subsurface material like this? Did you feel we are crazy? Yes, we are. We have to be crazier, actually not crazy, but challenging than bigger research institutes like NASA or the other big space agencies in the world. They are smaller. JAXA has a smaller team, but smaller budget must not mean smaller challenge. It must mean we can take higher risk for higher return. So in reality, even though it was too risky to make the spacecraft dive into 3-meter hole. So we tried to find a safe place to land around the crater where a rich deposit should exist. And we found two options at that time. The first option was what we call the S01 region, which is here, which looks smooth and safe for landing, but it is found to have less deposit from the observation. And the second option was the C01 region, which is here, which looks bumpier than the S01, but obviously a thick deposit exists there, according to thorough observations by multi-band cameras. And we had a lot of discussions from the viewpoint of science and technical feasibility and management risk. And you know, we have to go back to Earth with sample. If we fail in the second touchdown and lose the spacecraft, it means that we also lose the sample from the first touchdown. Can you accept that? On the other hand, the scientific value of the subsurface material and scientific value of the samples from multiple places are very, very big. And it was also a question of the risk of challenging versus not challenging. And how we, a not so big institute like JAXA or ISAS, can contribute to the planetary science of the world. So eventually we could decide to do the second touchdown to here. So this is called a C01B region, which has about 7-meter diameter, slightly larger than the first touchdown landing zone. And we evaluated it was technically feasible and the risk for it was acceptable enough. And besides that, it is scientifically the best place to land. So let me show you the movie during the final touchdown in the control room.
71、72、73、74、75、76、77、78、79。
Once you confirm the ascending, then we know that the spacecraft is safe. So there's a time to celebrate. Okay, now we succeeded in the second touchdown, like this. So it's the happiest moment. So now, is it the time to return to Earth? Actually, not yet. Hayabusa2's challenge does not end yet. And the second touchdown, after the second touchdown, we did another very delicate but scientifically important operations, putting 3 objects onto orbits around Ryugu to contribute to the gravity science. As at this moment, the 3 target markers were still left, and we put one target marker to an equatorial orbit around the asteroid, and another to a polar orbit around Ryugu. And also we put the 4th rover to another equatorial orbit around Ryugu, and which were all successful and delivered to the gravity science people. And this is showing the entire proximity operation activities for 1.5 years, and it was really a very busy period for us. And we did critical operations almost every 2 weeks. And I already talked about the rover landing and also the spacecraft landings and the kinetic impact operations. But to realize them, we needed to do additional critical descent operations for surface high-resolution surveys or for the guidance rehearsal. And also, besides such critical operations, we did many scientifically important observations from the high altitude, like moving to the side of the asteroid for terminator observation and to survey the north and the south pole and so on. And as a result, we did all the operations almost as planned, just slightly modification from about the number of the touching down because of the severeness of the surface. And we did 2 landings, 4 over delivery to the surface, and 1 artificial crater forming. And in addition, 3 objects were inserted to Ryugu orbits, as I showed in the previous slides, which is actually not in the original plan. And basically, we did a very serious engineering and the sciences. But besides that, one of the big fans of visiting a new celestial body for the first time is that we can name geological features as we like. So as we explored the Ryugu, we named the geological features like this. As the asteroid name Ryugu was named after a famous fairy tale from the ancient Japan, and so we named the geological features based on the world's fairy tales like Urashima Taro and Cinderella and so on. And actually 7 craters, 1 dorsum, and the 2 fossa and 3 saxa were named and authorized by the International Astronomical Union, or IAU. So we also gave nicknames to some of the important points for us, like landing points and the rover, spacecraft landing points and rover landing points. Although they are too small places to be authorized by IAU, they are emotionally very important places for us. So after finishing all these operations and activities, Hayabusa2 departed Ryugu on November 13, 2019. And these are the sequence of images taken while leaving Ryugu. The left movie was taken by the telescopic navigation camera, and the right movie was taken by the wide field of view camera at the same time. And this is almost the final shot. And after this, we turned off the cameras and turned on the ion engine, and we started heading toward the Earth. So I think this is the last one. So bye-bye, Ryugu. And then the return cruise took for 1 year. And the last 2 months required very precise guidance so that the spacecraft should land to a designated landing zone in Umera Desert, Australia. The re-entry capsule was separated from the spacecraft 12 hours before the separation re-entry, and it flew ballistically toward the atmospheric re-entry. And 1 hour after the separation of the capsule, the spacecraft itself diverted from the re-entry orbit so that it could escape from the Earth's sphere of influence and continue on to the extended mission. So I will show you the movie about that. So 12 hours before the capsule is separated to the re-entry corridor, and the spacecraft makes the full throttle burn to escape from the atmospheric re-entry trajectory. And on the other hand, the capsule flies toward the atmosphere and make a re-entry like this. And after that, the parachute is automatically deployed and softly descending to the desert of Australia, like this. And in parallel with the spacecraft, space side operation, we had to deploy about 100 people to wait for this capsule in Australia. And you know, this is 2020. It was right at the time of the COVID-19 started. But the actually Australian government and Australian Space Agency were so supportive to our mission, and they smoothly accepted our team to Umera Desert. So I will show you a short movie about the capsule recovery operation, field operation in Umera Desert. Okay, so in this way, we succeeded in the recovery operation, and the capsule and the samples in the capsule was transported to Japan. And then on December 15th, 9 days from the Earth reentry, we opened the sample container of the reentry capsule and found plenty amount of sample Ryugu. And our mission requirement was 0.1 gram. And we actually obtained 5.4 gram of a sample, 50 times higher than requirement, and which is the total amount from the first and the second landing. And this picture actually is showing the sample from the first landing. And we have another chamber which contains the one from the second landing. And we also succeeded in extracting gas sample from Ryugu, as you could see in the movie. And here let me show some of the typical Ryugu samples. The biggest one we could obtain is 1 centimeter size from the first touchdown, second touchdown, and from the first touchdown we got 5 millimeter size, the regolith, and that's really for us bigger than expected. And you can see very black regolith. Everything is black, and that reflected the existence of the carbon or organic compounds. And this is another pictures showing the big regolith actually analyzed by the Hayabusa2 project by ourselves. And here are some of the representative scientific outcomes from the Ryugu sample obtained through our sample initial analysis. Because we already spent 3 years from the landing, so we are gradually getting better and better science outcomes. And for example, the elemental abundance analysis here show that the Ryugu sample is very similar to the CI chondrite, which is the rarest type of meteorites. The Ryugu sample can be said the purest non-contaminated reference of the carbonaceous chondrite. And the other analysis show that the material in the sample has a clear evidence of water alteration. So there should be the chemical reaction with the water in the past. That tells us that the Ryugu's parent body has rich water in it. And we actually found the liquid water from the sample. That was really surprising also for us. And we also observed tiny magnetic field, and also we extract the gas, and so on and so on. So many scientific outcomes. And this also summarizes the scientific outcomes. And I already touched most of them, but I should mention that we confirmed about 20,000 molecules, which includes amino acids and even uracil. Uracil is a part of RNA. Although this uracil should not be derived from life-related reactions, it's interesting to see there are plenty kinds of life-related material in this deadly environment. And the recent analysis also show that about the chirality of amino acids. The amino acids found in the Ryugu sample has almost the even occupation between left-handed and right-handed ones. 50% left-handed, 50% right-handed chirality. And Earth-based life exclusively uses left-handed amino acids. So there's a difference. So this difference is also interesting to see and pursue, and which is not solved yet. And the outcomes keep expanding. And we gave 10% of the Ryugu sample to NASA. And NASA OSIRIS-REx mission will give us some portion of Bennu sample to us in return. in response. And it's really nice that the scientists in both countries can deal with the samples from 2 different asteroids. And I think this is the power of the collaborations and the nice things about doing similar type of missions by different countries in tight collaboration with each other. And OREX will return to Earth, the day after tomorrow. And so the Hayabusa2 team is awaiting for their success. And we also delivered a sample to the worldwide academia. 10% portion of the sample is planned to be delivered to researchers worldwide in AO basis. And for that, we opened the Ryugu sample database website. And everyone can access to this link. If you're interested in, please visit. You can even check it via your smartphone. And it looks like a catalog, just like an Amazon, although without price tag, of course, to show the individual sample with the size, weight, and some of the non-destructive analysis. And every 6 months, we open the AO to accept a proposal for sample analysis. And we have already delivered several tens of samples to international researchers. And we also delivered a sample to future scientists. We secured 40% of the sample to just store it in the controlled environment for the future generation, for future questions. I think this is another big significance of sample return mission, just like Apollo mission, and that this type of mission can open the door toward the future through the collected samples. Okay, going back to the engineering side, the Hayabusa2 spacecraft is still healthy. After separating the reentry capsule, Hayabusa2 continues its flight to head to 2 new asteroids, 2001 CC21 to flyby in 2026, and 1998 KY26 to rendezvous in 2031. And this extension should contribute not only to the new science in the new asteroids, but also to planetary defense technology and science. Okay, so Hayabusa2 mission was perfect success, and not only fulfilling the mission objectives defined beforehand, but we accomplished several engineering successes which had not been expected, partially thanks to the very harsh environment of Ryugu. And we succeeded in multiple rover activity on the asteroid surface and multiple landings and sample collections exploring subsurface, orbiting, and then returning a sample from the new world. Okay, let me skip the outreach and this one. Yeah, I want to mention about OSIRIS-REx that will return to Earth on this Sunday. So we have another great mission. OSIRIS-REx, of course, it will return to Earth the day after tomorrow, and it will return to Utah. And you can view I think you can view the live streaming by NASA, and that should be fun and spectacular. I will also fly there to observe it. So for our Hayabusa2 reentry, I calculated the reentry trajectory thousands of times, but I have never seen the deep space direct reentry with my eyes. As at that time, I was our reentry, I had to sit on the control room in Japan to manage the team. And so for me, this will be the first time to purely enjoy the deep space direct reentry with my eyes. And about the relation between Hayabusa2 and OSIRIS-REx, we have been in a good collaboration with the OREX team for a long time. And when both missions arrived at the target asteroids, we were surprised that 2 asteroids are so similar to each other. One colleague from OREX team asked me, "Did you really arrive at Ryugu?" And I answered, "I promise it is Ryugu. I calculated the trajectory of Hayabusa2 by myself, and I did not do such a terrible mistake." And OREX succeeded in landing and sample collection in 2020, but before that, they faced very similar problem as us because Bennu is very bumpy asteroid, just like Ryugu. And let me tell you a small story about that. We had a joint science meeting after the Hayabusa2 succeeded in that first touchdown, and before the OREX team attempted the landing. And there I I talked with Dante Roletta, the PI of the OREX team, and he said, if only OREX was equipped with the target marker. So as they don't have such equipment, they applied the natural feature tracking, which seems more sophisticated and difficult than the target marker-based guidance. Target marker is, artificial, so easy to process by onboard autonomy. But natural feature tracking has to deal with natural features, so which is apparently more difficult. And they finally succeeded in it. It was really incredible. However, at that chat, I responded to Dante. My thought was actually vice versa. What I thought is, if only Hayabusa2 was equipped with a longer sampler horn, like OREX's sampling arm, then our conclusion was, let's make the next generation small body sample return spacecraft together, which is equipped with target marker and longer arm. So this is exploration, and this is a challenge to unknown. So we cannot know how much length of sampling arm we needed before we actually arrive there. And we cannot know how effective the target marker is beforehand. So I'm so pleased that Hayabusa2 could demonstrate the big possibility of our technology, and I strongly hope that the more ambitious and more scientifically valuable missions will be born based on the Hayabusa2's achievements. And come back, OSIRIS-REx. Okay, Japan has several plans in 2020s, and a mission to Mercury, which is already ongoing, and also the lunar lander, which was launched a few weeks ago and heading to the moon for landing. And next year we will launch the Mars Moon Sample Return mission, MMX, and then the Phaeton flyby, the extinct comet flyby mission, Destiny Plus, will be launched after that. And we do not have an authorized plan for 2030s. I do not know if it's named Hayabusa3, but we hope to grow our sample return exploration technology more to the outer region of the solar system. Okay, so that's all I have, and thank you very much for listening. I'm very happy to answer any questions.
I think I speak for everybody when I say thank you for Hayabusa. Thank you for bringing the samples back to Earth, and thank you for giving a spectacular talk. We do have time for questions. As some of you know, but maybe not everybody, we have a procedure. There are people with microphones that will come to you when you raise your hand, and it's a kind of magical process, so just keep your hand up long enough for the microphone to finally arrive at you. They have different colors, windscreens, blue and red. I'll call on you by the color of the windscreen. When I do, please stand up, tell us your name, tell us if you're a member, and ask a question. Save the longer commentary for the social hour after the question and answer period. We do this because it makes the sound system work better. So we'll start with Kirby Runyon, the planetary scientist, with the blue microphone.
All right, good evening. Thank you, Yuichi-san. That was fascinating. Kirby Runyon, Planetary Science Institute. I am a member of the society. My question is about the gravity levels on Ryugu. What is the acceleration of gravity? And was the ejecta from the cratering experiment all retained on the surface, or did some of the ejecta escape, like we saw with the DART impact? Thank you.
Okay, thank you for the questions. And the gravity at the surface level is about 1/80,000 of the Earth. So it's almost zero gravity. So so as you said, most of the ejecta by the kinetic impact escaped from the surface of the Ryugu. But the variation or dispersion of the velocity are so huge, so some portion of the ejecta fell back to the surface, just a small portion. So most of the ejecta escaped, but just a small portion of the ejecta stayed on the ground, and we tried to pick that up.
Yeah, blue microphone.
Jim Caravala of World, non-member to my detriment. Wonderful presentation, huge inspirational, congratulations. What was the proportion of water that you might infer was on the asteroid from the samples?
What was the
Proportion of water that you think, if there was any estimates of the hydroxyl or water content on the asteroid?
So you mean where the water comes from?
No, I think
No,
he wants
no.
to know how much.
How much?
From
Okay.
your sample, what percentage, and then could you make a projected inference of what percentage of the entire asteroid?
Actually, I have no idea about the amount of water, and that should be an important number, but I don't have in my brain. Just a small portion as an absolute value, but which is definitely very larger than the ordinary stony asteroids. That's important. And in total, I don't have any idea about that.
Scott, red microphone.
My name is Scott Matthews, and I am a member. First, let me say this is the most spectacular scientific mission that I think I've ever seen in my entire life. My question is, in terms of the magnetite, do you know what the source of the magnetic field was that created the remnant magnetization? And then I have a second question that is probably a little more speculative. The fact that the chirality is equally left and right-handed in the amino acids, what does that have to say about life on Earth and its possible origins?
Okay, about the first question, the magnetite. Yeah, that means that the in the early era of the solar system, the material of the Ryugu is somewhere else, but very close to the sun, and that affects the magnetization. That should affect the magnetization, and after that. That material is accumulated to make the asteroid. So that tells us the early era of the solar system, the forming of the solar system, and also about the amino acid. Yeah, that's a good question. And what we found is that the mystery of the left-handed only of our life is found to stay mysterious. So the asteroid is very primitive and primitive body, and even in that kind of world, in such a world, the amino acid can be generated or created, but naturally. The chirality has to be 50%, 50 left and right. But after that, in the process of growing to the life, in some stage, a left hand is selected for some reason. So it's not from the origin. And we found what we found is the the left-hand side is the selection occurs in the after the stage afterward.
Is there a microphone somewhere? We have a question from the web.
We do have two questions from the web. The first question is from Eric from Sweden. Eric says, OSIRIS-REx used a crowdsourcing to map the surface of Bennu, which was also full of rocks. Did you consider a similar crowdsourcing approach for your mission?
Sorry, I couldn't catch the first part of the questions. OSIRIS-REx did what?
OSIRIS-REx used crowdsourcing to map the surface of Bennu, which was also full of rocks. Did you consider a similar crowdsourcing approach for your mission?
To make a map, you mean?
To map the surface.
So we did mapping, of course, and the first thing we did is to observe the whole asteroids from the distance, like 20 kilometers. But of course, it's not enough resolution for landing. So for that, we try to go to a lower altitude to get higher resolution images. One of the big differences between OSIRIS-REx and the Hayabusa2 is that OSIRIS-REx has higher resolution camera. That was actually envy for us. But our spacecraft is very compact and a multi-objective camera. Like we use the same camera for navigation and also the scientific objective. So we have to do we have to compromise the resolution versus the field of view. And so what we did, different from the OSIRIS-REx, is we frequently went down to the lower altitude to observe with the higher resolution to identify where the safe place is. But anyway, the strategy for making the map, making the map is very important process before doing the landing.
I think there's another part to his question. He wanted to know if you released the data to the public and allowed them to analyze and provide you with suggestions, so-called crowdsourcing.
Crowdsourcing. Okay. Yeah, we already opened the Ryugu data to public, and anyone can access to it. So that's a science data policy of us. But we actually did not do the crowd science yet, and we actually opened our data more than 1 year after we got the data. One of the reasons is to protect the scientists and in the mission that contributed to the mission directly. But the more important one is that we are a smaller team. So we are very busy, and we have to concentrate it on. We have to go focus on our own job, and crowd science is very important. But the source of that is opened, like more than one year after we get. I think that's the difference.
Yeah, we were talking about another difference in mapping, right? The famous rock musician Brian May is also a pretty well known at this point astrophysicist, but he has this interest in stereoscopic imaging, and he offered his services to the OSIRIS-REx team, and they actually did produce stereoscopic images that were, it turned out, according to the PI, Dante Loretta, was quite useful in figuring out where to land on Bennu. And there's a very nice book you might like to buy on Amazon that provides a very nice description of OSIRIS-REx and has many of the stereoscopic images they used. So it's kind of funny because you couldn't do that, but you did talk to Brian May, right?
Yeah, actually, yeah. We also have a very good collaboration with the Brian May, and so what we couldn't do is we opened to public very rapidly,
Right.
but we opened to Brian May by letting them join our science team. So he is actually one of the science members of.
I believe you said that had some benefits. You got to go to a concert or two.
No. So our policy is to try to open our science activities as much as possible, but not open to infinite, but to open
I think
to
that's a good
the experts.
benefit. It's good morale builder, right? All right, where is it? Another question from the web, blue microphone.
We do have another question from the web. David Rabinowitz, who's a PSW member, says the first Hayabusa mission led to the production of a feature film. Will there be a film about the Hayabusa2 mission?
Feature
A film?
film. Okay.
Movie? Yep.
Yeah. Yes. As you said, the Hayabusa 1 was in the 3 movie films, big films, and the reason for that is very dramatic in terms of human activity, and it faced many engineering troubles. But for Hayabusa 2, because most of the trouble is scientific one, not engineering one. Engineering, it seems from the outside, it's very smooth. So movie film is not. We are not offered any movie films yet. Yeah, but that's why I am here. So if someone watch my presentation, and if you like to make a movie, please call me. But I try to tell you the real hardship, real challenge that we faced, and I hope you can feel somewhat about that.
I think we do. Red microphone.
Yes, Timothy Thomas. I'm a member of the society. I'm wondering about the asteroid itself. Is this parent body sent out a rock that then accumulates these boulders, or is it boulders all the way through?
Yes, yeah, that's a good question. Yes, as you can see, the shape of the asteroid is very like a top shape, and it's a typical shape of made by the regolith accumulated by the very small gravity with each other, and because of the high spinning, the shape of it gets like that afterward. And also from the density and measured by the gravity and also from the size, the asteroid is found to be very porous. So there's many spaces between the regolith and regolith. That means that the regolith is connected very weak with each other, and that means that the Ryugu was born. Ryugu was made by the many regoliths flying in the vicinity in the space, and that should come from the other parent body. And we actually found from the spectrum analysis that the parent body of the Ryugu should be 2 candidates in the main belt. So we actually identified 2 big asteroids in main belt, Polana and Euralia, and this should be the parent. This should be the parent of the Ryugu. But actually, in what I said about the outcomes of science, one of the outcomes of science, scientific outcomes, the water is found, then there should be a huge water alteration. And you know, the asteroids in the main belt does not have ocean. And this means that the asteroids in the main belt is still a child of the other parent body, and that should be destroyed by some reason during very long in the very long history of the solar system. And in the ancient, very long time ago, the origin of the material of Ryugu should be in the water world of some of our planet that does not exist. So that's one of the theory or one of the estimate, but that can explain what we found.
Blue microphone coming to the front here.
I'm Bob Hershey, I'm a member. What were the differences you found from Hayabusa and OSIRIS-REx?
What was it?
Differences you
Difference. Many differences. So first of all, about the cruising, we used ion engine, and they use chemical thrusters. Because the OREX is a 2-ton, and out of 2-ton, half of it is a propellant. If you can make the spacecraft with that size, you can do that. But we have to make the spacecraft compact for many reasons, mostly from the budgetary reason. And the spacecraft has to be very compact, and for that, the propulsion system has to be very efficient. So we applied the ion engine system. And also about the landing strategy, sample collection strategy, I mentioned about the difference between target marker and natural feature tracking. But after that, the method of collecting the sample from the surface, it looks very similar between OREX and the Hayabusa2, but they are actually totally different. We use the projectile to shoot the ground, to destroy the ground, to collect the sample. But the OREX spacecraft use the gas to blow the surface, and the small regolith can fly by that gas blowing, and then collect them. So it's a numeric sampling, so it's based on gas, but we are based on the projectile shooting, kinetic reaction. So these are big differences.
Were there any high molecular weight organic compounds that you found? I mean, high molecular weight organic compounds? Much higher molecular weight than, say, amino acids or...
Besides the amino acid, we found many different types of molecules, organic compounds. So heavier than amino acids.
Heavier, more complex.
More complex one. So many scientists are analyzing that. I do not know the detail, but the more heavier than the amino acid, many of them are found.
And did I understand correctly that these asteroids are spinning, and that accounts for their shape, and that's why Bennu and Ryugu look similar?
Yes. The top shape is very typical and actually famous among the asteroid scientists. Theoretically, we had not seen the top-shaped asteroid, but we knew theoretically from the numerical analysis that that kind of top shape is one of the stable shape for the very sparse, highly porous asteroid from the how can I say the theoretically from the analysis.
Yeah, right.
But what we found that so the Hayabusa2 OSIRIS-REx, the target Bennu, was known to be a top shape before they arrived there because of the later observation. Now, by the radar observation, we could sometimes very precisely estimate the shape, measure the shape of the asteroid from the Earth. But for Ryugu, we had not such a chance because of the celestial geometry of the Ryugu. But finally, we arrived at Ryugu before the OREX arrived there, and found that the top shape, so that it is top shape. So actually, the Ryugu is the first asteroid to be found as a top shape asteroid.
Are there any other questions? If there are, please raise your hand. Seeing none, I think we will close the question and answer period. And before you go, we want to say thank you and give you a small tokens of appreciation, including a framed copy of the announcement of your talk, our PSW rosette, which we hope you'll wear and explain to people what it is. It's kind of free advertising for us. And a copy of Volume 1 of the Philosophical Society of Washington Bulletin, which tells you, among other things, who founded the society and why they founded it. But more interesting to us in the current times we live is a very nice statement about how science proceeds and how scientists should behave with regard to one another and what scientific discourse is supposed to be like, which is sometimes quite adversarial, but with an open mind. And so I would hand these to you, but it gets to be awkward, so I've taken to showing them. And they are really over here. I promise I will give them to him. And I thank you very, very, very much.
Thank you very much. Thank you very much.
Before you all leave, we will, of course, be having somebody come and talk on OSIRIS-REx in due course. I'm trying to get Brian May to come, but my chances of doing that are probably pretty slim. I might have to steal his guitar and tell him I'll give it back if he comes and talk. So, the next meeting, number 2482, will be on October 6th. And provided that our friends on Capitol Hill have such a hard time figuring out how to spend $4 trillion a year and do not argue it so badly that they shut the government down, the speaker will be Lori Locascio. That is not political comment. Director of the National Institute of Standards and Technology and Undersecretary of Commerce for Standards and Technology. And she will be discussing, I believe, infrastructure and research at NIST. And I think it'll be an interesting talk. And I think it's important for the public to know what the infrastructure problems are at that institution, which is extremely important to commerce and science in the United States and in the world. The 2483rd meeting will be on October 20th. The speaker will be Pri Narang. She is a professor in the Department of Chemistry and Biochemistry at UCLA. She'll be speaking on quantum communication and networks. and maybe on some aspects of quantum computing. Number 2,484 will be on November 3rd. The speaker will be Ted Schultz from our own neighborhood. He is curator of Hymenoptera at the Smithsonian National Museum of Natural History. As many of you probably know, Hymenoptera comprise the ants, wasps, bees, and sawflies. There are over 150,000 known living species of Hymenoptera and 2,000 that are known to be extinct. Many of these species are agriculturalists, and Ted will be speaking about the convergent evolution of agriculture. Humans, as we'll find out, are far from the only farmers, and the ants are actually quite clever in how they farm. The 2,485th meeting will be on November 17th. The speaker will be Bob Truog of Harvard. He will be speaking on defining death, science, medicine, belief, and law. In part, because of differences in legal definitions, a person legally dead in California may actually be legally alive in New Jersey. And there's actually an actual case in this where a family had a daughter who was legally dead in California, and they didn't want her to be legally dead. They thought maybe she would come back to life. And so they moved her to New Jersey. The subject involves, of course, complex myths of competing viewpoints of politicians, lawyers, scientists, doctors, cultures, religions, philosophers, and ethicists, and is a microcosm of how these differences might be reconciled and sometimes are not in a democratic, diverse, and multi-jurisdictional society like ours. Please check the PSW website for up-to-date information on meetings and lectures. To all of our donors for sponsoring series and individual lectures, we have thanks. These sponsorships are crucial to the society's financial well-being. Without them, the society would have to substantially curtail its activities and have far fewer lectures each year as we continue to face increasing costs. As you've heard from me, the Cosmos Club, our home for 125 years, tripled our costs last year. We did very well last year, partly because only half the year was at the increased costs. This year, all of our meetings will be at the increased costs. So I hope the Society will be as fortunate this year as it was last year in sponsorship support, and that we will again be able not only to meet dramatically increasing costs, but also to exceed them. If you're interested to be a sponsor or add to your sponsorship contributions, please come see me. You can email me, you can call me, you can waylay me in the hall. I will be happy to talk to you. Finally, let's thank our crew for producing this meeting, streaming and recording the program, and editing and posting the video to the PSW website and the PSW YouTube and Vimeo channels. Janice Soreth for greeting and room management, Cameo Lance for writing the minutes, and Mark Clampin for reading them. I didn't have his name in advance, so he's not on the slide here, but no less credit to him. Robin Taylor, always back there where you can't see her, for doing video, the sound, and the live stream. Ann McQueen for handling the chat on the live stream. Andrew Gunn and Jared McQueen for running the cameras. Bill Mitchell hasn't done anything yet, but he will be editing the video. Please join me in giving them all a warm thank you. Before you go, please remember to return your name badges to the plastic bin in the back. And with that, I will entertain a motion to adjourn the 2481st meeting. Second? All members in favor? All members opposed? Okay, the meeting is adjourned to the social hour in the back of the room. Enjoy the cheese and apple cider.